Today we're going to cover Section 2 and Section 3 of Chapter 17. So starting with Section 2, Properties of Mechanical Waves. The first term is periodic motion. It's any motion that repeats at a regular time interval. And when you have a motion that is repetitive, you have also what's known as the time period. So that's any amount of time that's required for one complete cycle before that object or that motion returns to its starting point. So for example, if you make a mark on your bicycle tire, the time it takes for that to make one complete cycle back to its original position is the period. And of course, because period is time, it is measured in seconds. We also have what's known as the frequency. It's the number of complete cycles in a given time frame. So if it is, maybe you can make one complete cycle every minute, well, that would be 60 cycles per second. All right, because there's 60 seconds in 1 minute. The frequency of an object depends on the source that's producing the frequency. And we measure frequency in cycles per second or in the abbreviation of hertz. So capital H, lowercase z. So if you see 10 hertz, that means frequency. Frequency is also represented by a lowercase f in the formula, and we'll get to that in just a minute. Wavelength is another important thing. Obviously, it's a length, so it is a distance between a point on one wave and the same point on the next cycle of a wave. So from crest to crest, from trough to trough, or from resting point to resting point. So here's an example of crest to crest. Wavelength is going to be measured in meters, so lowercase m because it is length. And in our formula, we're going to represent wavelength with a Greek letter, looks like an upside down Y. This is lambda, Lambda, lambda. We also have wave velocity, and we've talked about velocity before from chapter 11. But wave velocity is going to depend on two things: distance, or what we call wavelength, and the time it takes, or the frequency. So how do we calculate wave velocity? We're just going to multiply the distance by the frequency. So wavelength multiplied by frequency. Or lambda multiplied by f. Let's take a look at an example. One end of a rope is shaken to produce a wave with a wavelength of 0.25 meters. The frequency of the wave is 3 hertz. What is the velocity of the wave? Well, here's our formula. Velocity equals lambda multiplied by f. Our lambda, our wavelength, is 0.25 meters. Our frequency, our f, is 3 hertz. So 0.25 meters multiplied by 3 hertz. Well, 0.25 multiplied by 3, you should get 0.75. And because this is a velocity, we are still using meters per second. Now for a practice problem on your own. A wave on a rope has a wavelength of 2 meters and a frequency of 2 hertz. What is the speed of the wave? All right, last concept for section 2 is amplitude. The amplitude is the maximum displacement of a medium from its resting point, or of that wave. So the more energy a wave has, the greater the amplitude, or the farther away those wave crests and troughs are going to be from the resting point. All right, moving on to section 3, and this is very short, the behavior of waves. How do waves behave? First way is that they can be reflected. So this is when a wave bounces off of a surface that it cannot pass through. Reflection does not change the speed or the frequency of a wave. So what you're putting in is what you're getting back with reflection. Refraction, however, is the bending of a wave as it enters into a new medium at an angle. So for an example, light going from air to water. I'm not sure how many of you have ever used a straw in a clear glass, but if you were to insert a straw into a glass of water, you can clearly see that the straw looks like it's broken or bent and that is because of how light is refracted between air and water. So one side of the wave will move more slowly than the other. So in this case, your speed changes. We also have what's known as diffraction. It's the bending of a wave as it moves around an obstacle or passes through a very narrow opening. And then we have interference. And there are two types of interference. With interference, you have two or more waves that overlap and combine. Well, you can have constructive, which means they construct or build each other up to be a bigger wave, or you can have destructive, which is destroying each other to where there's little to no wave left at all. So again, constructive, you have a larger wave that's produced, and destructive, you have a smaller wave that's produced. And when you guys get to do the computer lab, and this is the last computer lab for the semester, the computer lab will clearly show you the difference between constructive and destructive. And that's it for today.